Imagine waking up at like 3 in the morning, your pager is just buzzing relentlessly.
Oh, the absolute worst case scenario.
Right. You log into your terminal and the situation is grim. The primary server CPU is pegged at 100%, the storage arrays are just grinding, and suddenly, boom, your SSH session completely drops.
Ouch. Yeah, you're locked out of your own infrastructure at that point.
Exactly.
Yeah.
The only thing standing between you and explaining a catastrophic data wipe to your organization is, well, a recovery file you set up and hopefully tested like 6 months ago.
And that right there is the exact moment where system administration stops being this abstract engineering exercise. It turns into a high-stakes rescue mission.
Yeah, totally.
Because when the foundation cracks, the theoretical knowledge of how you built the system matters a lot less than the practical tools you actually have in place to keep it alive. So today, we are focusing heavily on those safety nets.
And to do that, we are pulling our framework for this deep dive from a highly specific environment. We're looking at Class 9 of a Spring 2026 System Administration course.
Right, CS123, it's Skidmore College.
Exactly, taught by instructor Dave. And just to give you, the listener, the technical context here, the students in this course, they are running Fedora Linux on KVM.
Which stands for Kernel Virtual Machines, for anyone wondering.
Right. So they aren't just managing like lightweight cloud containers. They are dealing with hardware virtualization baked directly into the Linux kernel itself.
Yeah, it's serious stuff. And up until this point in their syllabus, they've really been constructing. They've formatted drives, they've mounted file systems, launched services.
So Class 9 represents this hard pivot in their education.
It really does. It marks the transition from that relatively safe construction phase to, well, the continuous warfare of survival.
Survival mode.
Exactly. The course material for this week really zeroes in on how you monitor system behavior invisibly, how you engineer disaster recovery mechanisms that actually work, and how you defend against the invisible, relentless decay of your software stack.
Which is so critical, and the bedrock of that survival is knowing exactly what happened in the moments leading up to that 3 a.m. crash we talked about.
Right, you need the timeline.
Yeah. I like to think of it like an aircraft. If the operating system is the airplane, the /var/log directory serves as its flight data recorder.
That's a great analogy.
But, treating logs merely as a post-crash black box, it severely limits their potential. In a well-designed architecture, those logs are your live instrument dials.
Spot on. In the Linux ecosystem, the operating system tracks its own operations through system accounting. Think of it as an immutable ledger.
Okay, a ledger.
Yeah, it records when a user escalates their privileges using the sudo command, or when a critical daemon starts up, or, and this is the big one, when a disk begins throwing silent read errors.
Oh, the silent errors will get you.
They absolutely will. But historically, the philosophy of how that ledger is maintained has fractured a bit. Today, you have the modern accounting system powered by audit.
Right, and that writes its data to /var/log/journal, right.
Exactly. Yeah. But running parallel to that, you still have the legacy Urzilog daemon, and that pushes your traditional system messages into /var/log/messages.
Okay, got it.
And then, for tracking hardware utilization over time, you have the sysdat utilities capturing metrics in /var/log/say.
So this divide between audits, journal, and traditional logging, it introduces a really fascinating architectural debate.
It does.
Because if you look at third-party services like the Apache web server or Samba handling Windows networking, they still default to writing plain text files directly into the /var/log tree.
Right, they stick to text.
And the appeal of plain text is obvious, right? It's universally accessible. You can pipe a text log through a basic grep command. You can parse it with awk, or just read it natively without any specialized decoder.
Which is super convenient.
But then modern Linux distributions made this deliberate choice to shift the core operating system journal into a compiled binary format. So if plain text is so incredibly flexible, locking your most critical system data behind a binary structure seems, I don't know, kind of counterintuitive.
I mean, I hear you, but the transition to a binary journal was really driven by the sheer scale and complexity of modern operating systems.
Okay, how so?
Well, plain text is fantastic when a human sysadmin is just casually reviewing an Apache access log. But a kernel generates a staggering volume of highly structured rapid-fire data points.
Right, thousands of events a second sometimes.
Exactly. By storing the journal in a binary format, the system can instantly index that data and attach rich metadata to every single entry. You aren't dealing with a flat text file anymore. You are essentially interacting with a high-performance database.
Oh, that makes sense. Which fundamentally changes how you interact with the information. Because it operates like a database, you rely on the journal untokettle command to query it. You don't have to write these, convoluted regular expressions to filter out background noise. If you suspect your secure shell service is under a brute force attack, you simply pass the unit flag by typing journal-kyle-usd.
Yep, it's that easy.
And the binary index immediately isolates every log entry generated by that specific daemon. Or if you want to monitor the system state as it happens, adding the dash flag tells journal-kyle to follow the live output, right? Instantly streaming new events to your terminal.
Right, and the strategic value of journal-kyle lies in that proactive observation. You monitor those logs to catch the anomaly before it cascades into a full-blown disaster.
Right, you're looking for the smoke before the fire.
Exactly. You are actively scanning for the subtle warning signs, like a memory leak slowly consuming your RAM or an application silently failing to write to a database. The goal is to reinforce this structure while it is still standing.
But inevitably, despite your best monitoring, a critical failure will occur. You might query the journal and discover that, well, a malicious script just finished encrypting your primary storage array.
The absolute nightmare scenario.
Yeah. And the logs will provide a meticulous timeline of the compromise, sure, but they possess no mechanism to decrypt your data.
No, they don't.
When the infrastructure is fundamentally compromised, observation is useless. You need the ability to reverse time.
And that brings us to the time machine. Disaster recovery is entirely contingent on the architectural integrity of your backups.
Happiness is an up-to-date backup, right?
That's the saying. In the IT industry, an infrastructure without a functional backup is not a question of if it will fail, but simply when. And the course material introduces the foundational backup schemes that dictate how that data is captured: full, differential, and incremental.
Okay, let's break this down. A full backup is pretty self-explanatory. It's the baseline, a complete bit-for-bit snapshot of the target data.
Right.
So assuming an administrator runs a full backup on Sunday, the architectural decisions really begin on Monday. A differential scheme captures every single change made since that initial Sunday full backup.
Correct.
An incremental scheme, however, only captures the changes made since the very last backup of any kind.
Exactly. And the strategic choice between differential and incremental backups forces you to balance recovery speed against storage capacity.
Right, because if you employ a differential scheme and your server implodes on Friday afternoon, your recovery path is remarkably fast.
Super fast. You restore Sunday's full backup, and then you just layer Thursday's differential backup right on top of it. 2 steps, and your system is live.
But the cost of that speed is that Thursday's differential file is massive because it contains all the accumulated changes from Monday, Tuesday, and Wednesday.
Exactly.
Yeah.
Now, conversely, an incremental scheme generates tiny, highly efficient daily files. But restoring that same Friday crash requires this really tedious, fragile chain.
Oh, right.
You must apply Sunday's full backup, then sequentially apply the incrementals from Monday, Tuesday, Wednesday, and Thursday. And if just one of those intermediate files is corrupted,
the entire recovery sequence fails.
Yep, it's completely broken.
Wow. And managing the sheer volume of media required for these schemes introduces rotation strategies. Like, the grandparent-parent-child model is the industry standard, right? Maintaining full backups at annual, monthly, and weekly intervals.
That's the one most people know.
But the Skidmore syllabus explicitly highlights the Tower of Hanoi rotation scheme, which, when I saw that, I laughed because the name originates from that classic mathematical puzzle. You know, moving the wooden discs across 3 pegs without ever placing a larger disc onto a smaller one.
Right.
Mapping the mechanics of a wooden puzzle to digital tape drives feels, I don't know, highly abstract to me.
It is abstract, but mathematically it's brilliant. The Tower of Hanoi strategy applies a recursive algorithm to the rotation of your backup media.
Okay, walk me through it.
Imagine you have a limited pool of backup tapes. Tape A is utilized every other day. Tape B is utilized every 4th day. Tape C is written to every 8th day, and tape D every 16th day.
Oh, I see.
Yeah, by staggering the overwrite schedules mathematically, this rotation yields an exponentially growing historical archive using a shockingly small amount of physical media.
So you sacrifice the ability to pull a specific daily snapshot from, 3 months ago, but you gain a reliable, staggered timeline of recovery points stretching far into the past.
Exactly, without bankrupting your IT department on hard drives.
Which is always a plus. Now, executing these rotation schemes requires specific, highly reliable utilities. While the enterprise market is flooded with proprietary backup suites, Dave's CS123 class grounds the students in the native foundational Linux tools.
Which is the best way to learn.
We're talking dump, restore, tar, and rsync. The dump utility operates on a strict numeric tier system ranging from level 0 to level 9, right?
It does, and these levels map flawlessly to the backup schemes we just outlined. A level 0 is your full backup. A level 1 acts as an incremental, backing up everything that changed since the level 0.
And the resilience of dump comes from how it maintains state. Because by passing the -U flag during execution, the utility automatically updates a human-readable ledger located at /etc/dump dates.
Right.
So the operating system inherently knows the precise timestamp of its last successful backup without needing to manually scan the entire file system.
Exactly. And when a disaster necessitates pulling that data back, the restore utility acts as the inverse mechanism, is incredibly versatile.
Yeah, how does that work?
Well, an administrator can invoke restore-R to completely rebuild an entire file system onto a freshly partitioned drive. Alternatively, they can invoke restore-C to simply compare the contents of the archive against the live file system to verify its integrity.
Oh, that's handy.
Yeah, or they can even drop into an interactive shell using restore-I to navigate the archive like a directory tree and extract just a single accidentally deleted file.
Which saves so much time. Then we have the tape archive utility, universally known as tar. It bundles complex directory structures into a single cohesive file and natively supports lossless compression algorithms like JIP to minimize the storage footprint.
tar is a classic for a reason.
But looking at these archival tools introduces a significant philosophical question regarding workflow. Because we have rsync,
I think.
the rsync utility is legendary for its efficiency. It synchronizes directories by calculating the delta transferring only the specific bytes that changed,
Right.
and the resulting backup is not an abstracted archive. It is a fully readable one-to-one directory structure. An administrator could simply configure a nightly cron job to sync their primary drives to an external server. So I have to ask, why should anyone burden themselves with the complex levels of dump or manage compressed tar archives when rsync effortlessly creates a perfect browsable clone of the environment?
That is such a good question. And relying on a pure synchronization tool like SureSync as your primary backup mechanism is a devastating trap.
Wait, really? A trap?
Yes. RiSync is a brilliant utility for mirroring data, especially with flags like --delete-before or --dry-run. But a mirror is fundamentally not a time capsule.
Oh, I see where this is going.
Right. Consider a scenario where an attacker compromises your database on Tuesday and silently drops your most critical tables. Or maybe a misconfigured script corrupts your vital configuration files. The server is compromised, but it is still running.
Okay.
When your automated nightly rsync job executes on Wednesday morning, it will scan the source drive, observe that those files have been deleted or altered, and meticulously replicate that exact destruction onto your backup drive.
Wow. So the mirror simply reflects the disaster. You have essentially automated the erasure of your own safety net.
You have perfectly synchronized the corruption.
That's terrifying.
It happens all the time. Archives generated by dump or tar serve a distinctly different architectural purpose. Immutability. They freeze a specific moment in time within an encapsulated file. If your system is compromised on Wednesday, you can access Monday's compressed tar archive and extract the uncorrupted data.
Which you cannot perform from a mirrored directory that just obediently overwrote Monday's pristine state with Wednesday's catastrophic failure.
Exactly. And that conceptual trap perfectly underscores the golden rules of disaster recovery, emphasized in the course notes.
Right. First, backups must be encrypted at rest, ensuring that stolen physical media does not result in a data breach.
Step.
Second, they must be stored off-site, guaranteeing that a localized disaster like, say, a server rack catching fire doesn't incinerate both the primary array and the backup drive simultaneously.
Yes. And third, the foundational rule highlighted by a Toy Story meme embedded in Dave's lecture slides.
Oh, I loved this part. The image features those little green aliens staring upward in reverence, and it's captioned with the sysadmin's greatest anxiety. Backed up last night. Did you test it?
Yes, because a backup that has not been empirically verified is merely a theoretical concept.
Wow, that's a great way to put it.
The IT landscape is littered with post-mortem reports of organizations that faithfully ran backup scripts every night for years, only to discover during a ransomware event that their encryption keys were lost or the tape drives had silently misaligned.
Oh, that's brutal.
If you have not actively restored the data to an isolated testing environment, booted the applications, and verified the integrity of the files, you do not possess a backup. You possess a dangerous illusion of security.
Testing the restore is the only mechanism to mathematically prove the safety net exists.
Exactly.
But, engineering backups is fundamentally a reactive posture. It dictates how you recover after the armor is pierced. Let's pivot to the proactive side of system administration, defending the perimeter against software rot.
Software rot.
The phrase software rot evokes this visceral image of physical decay, like leaving a sandwich in the fridge too long.
Right, like organic matter degrading over time.
But compiled binaries are static. A web server binary compiled in 2021 contains the exact same sequence of ones and zeros today. It doesn't organically decay. So my theory is, software doesn't rot. The world around it just gets more hostile.
You nailed it. The code itself remains immutable, but the ecosystem surrounding it evolves into an increasingly hostile environment.
Yeah.
A piece of software written 3 years ago was engineered to withstand the specific threat landscape of that exact moment in time. Fast forward to today, and security researchers, along with malicious actors, have mapped out entirely new buffer overflows, privilege escalation vectors, and cryptographic flaws.
Not to mention the underlying hardware evolves.
Right. Running untouched, unpatched software is akin to utilizing a nautical map from 1950 to navigate a modern coastline. The map itself hasn't rotted, but the physical world it represents has drastically changed, making reliance on it incredibly dangerous.
Which means mitigating that environmental hostility requires aggressive, continuous patching. The administrator must continuously apply updates to patch logic bugs, close newly discovered vulnerabilities, and ensure compatibility.
And in a compliant Linux environment, attempting to execute this manually is completely unsustainable.
Oh, I can't even imagine.
Locating a security patch, downloading the source, compiling it, and then suddenly realizing the new version requires 3 other updated system libraries to function. It creates an impossible cascade of dependencies.
Dependency hell.
Dependency hell. That is exactly why automated package managers are the cornerstone of modern server maintenance. Within the Fedora environment utilized by the Skidmore students, the default package manager is DNF.
Which stands for Dandified YUM, right?
Yeah.
The next generation of the Yellow Dog Updater modified. Though I know other distros use alternatives like apt.
Right, and DNF programmatically maps and resolves that entire web of dependencies. It abstracts the complexity away from the administrator.
So you can run DNF list to audit the available software repositories, utilize DNF search to locate specific administrative tools, and trigger DNF install to deploy them cleanly.
Exactly. But the absolute critical command for combating software rot is DNF upgrade.
That's the big one.
Invoking that single command forces the system to compare every installed package against the remote repositories, identify newer secure versions, and orchestrate a safe, system-wide upgrade of the entire stack simultaneously. It is the most effective proactive defense available.
Because by relentlessly patching the software, you actively shrink the available attack surface, closing known vulnerabilities before automated exploit scripts can weaponize them.
Precisely.
So understanding the underlying philosophy of system logs, backup immutability, and dependency resolution is vital. However, executing those concepts without bringing down a live production environment is the ultimate crucible, and that is exactly what Dave's students must prove this week in Lab 9.
The architecture of Lab 9 is intensely practical, and it is heavily emphasized in the syllabus as a graded assignment due next Wednesday at 3 p.m.
Don't forget the deadline.
Right. It demands that the students synthesize these isolated concepts into a unified professional workflow.
So they begin by addressing the software rot. They're instructed to run DNF-refresh upgrade. The lab notes actually explicitly tell the students to be amazed at all the updates since January.
Which is such a great exercise. It serves as a stark visual demonstration of the velocity of software decay. In just a few short months, a fresh operating system install accumulates a massive backlog of critical security and stability patches.
And once the rot is patched, the lab forces them into disaster recovery engineering. They must utilize their administrative privileges to provision a new virtual disk with sufficient capacity to house backups of their virtual machines, /etc., and /home directories.
But they're not permitted to simply format the drive and blindly copy files.
No.
They are required to initialize, construct, and mount a fully encrypted file system on that virtual disk. This forces them to practically implement the golden rule that backups must remain secure even if the storage medium is compromised.
So following the encryption, they utilize either tar or sync to back up those critical directories.
Yeah.
But the brilliance of Lab 9 is that it refuses to let the students stop at the creation phase.
Yes.
It forces them to directly confront the anxiety of the Toy Story meme. If a student chooses to construct an archive using tar, they are mandated to create a completely new directory structure, specifically /root/restoredist, and extract their archived files into that isolated location.
That is the defining step of a professional system administrator. But they aren't merely performing a visual inspection to see if the files appeared. They are required to execute the diff command.
Oh, diff is ruthless.
It is. Diff systematically analyzes the contents of the /root/restoredist directory against the live /etc. and /home directories. It scans the actual payload of the files byte by byte. If the diff command returns 0 output, it mathematically proves that the extraction is a flawless, uncorrupted replica of the original state. They are empirically validating the integrity of their safety net.
It perfectly solves the "did you test it" problem. It engineers muscle memory for the discipline of testing restores. And examining the broader course calendar, establishing that discipline foundation is critical because the environment is rapidly increasing in complexity.
It really is.
The syllabus schedules a series of quick explainer presentations where students must master and demonstrate specific utilities to their peers. Like, Antran is tasked with breaking down file permissions, Jack is presenting on the complexities of GARGs, and Ryan has an upcoming technical slot as well.
Having to articulate a technical concept to your peers exposes any gaps in your own comprehension immediately.
Exactly. It essentially crowdsources the expansion of their administrative toolkit, and they will desperately need those tools during server deployment night, scheduled for Thursday, April 23rd.
Oh, server night. The parameters for that deployment night are intense.
Very. From 5 to 8 p.m., the cohort is tasked with architecting and deploying a server configured to operate as a routing firewall for a multi-zone network.
Setting up multi-zone firewalls while eating pizza. I mean, that is the peak college computer science experience right there.
Honestly, yes. But when you begin managing live traffic across distinct security zones, the integrity of the logs and the reliability of the backups we've discussed become exponentially more critical. The margin for error just vanishes.
Though, as you said, they will be heavily provisioned with pizza and soda, which remains the universally recognized high-octane fuel for surviving complex infrastructure deployments.
Naturally. And that hands-on crucible directly prepares them for the student script demos on Wednesday, April 29th.
Right, in those demos, the students present the bash scripts they've engineered throughout the semester. Writing custom scripts to programmatically automate your log parsing or orchestrate your encrypted backups is the defining characteristic of a maturing sysadmin.
Because you transition from manually executing repetitive tasks to programming the infrastructure to govern itself.
Exactly.
So let's synthesize the core architecture we've explored today. Transitioning a server from the initial build phase to surviving in production demands a fundamental shift in operational mindset. You must treat your /var/log directory not as a graveyard of errors, but as a live instrument panel, leveraging journal2all to isolate anomalies before they cause a critical fault.
Right.
You must aggressively combat software rot by utilizing package managers like DNF to automate your patching workflow. You must recognize that mirroring tools like rsync simply replicate your disasters, making immutable archives and offsite encryption vital.
Yep, the time machine.
And most crucially, whether you run enterprise infrastructure or you are completing Skidmore's Lab 9 by Wednesday at 3 p.m., you must mathematically verify your restores. A safety net you haven't tested is a net that does not exist.
It requires an unyielding level of discipline. But, before we conclude, I want to present one final architectural puzzle for you, the listener, regarding the mechanics of these safety nets.
Ooh, a puzzle. Let's hear it.
The course notes outline a scenario where an attacker compromises your system and deploys ransomware. The prevailing wisdom states you must patch the vulnerability before you restore your backups, or the attacker will simply exploit the exact same vector a second time.
Right, you have to permanently seal the breach before you attempt to rebuild the infrastructure. Otherwise, you're just putting out a welcome mat for them to come right back in.
Exactly. But consider the operational timeline. Your entire ability to forensically determine how the attacker breached the perimeter relies heavily on analyzing the system logs.
Okay.
If those system logs are stored natively in the /var/log directory on the precise server that the attacker just gained root access to, What mechanism prevents the attacker from simply purging or manipulating their own log entries before launching the ransomware payload?
Oh, wow. Wait. If they achieve super user access to the system, they achieve write access to the flight data recorder.
Yes.
You are essentially investigating a bank robbery where the thieves have root access to the security camera footage.
They completely control the narrative of the attack, which introduces the critical enterprise concept of log shipping. Relying exclusively on local storage for your system diary creates a massive single point of failure.
So what's the solution?
Robust architectures configure their daemons to stream those journal entries over the network in real time to a hardened, isolated, append-only log server.
Okay.
Even if the primary application server is completely compromised and the drives are zeroed out, the forensic timeline of the breach is already locked securely in a vault the attacker cannot reach.
Because it's on a totally different machine.
Exactly. It is the ultimate realization that your diagnostic mechanisms cannot reside on the very hardware they are tasked with monitoring.
That concept completely reframes how you design resilience. The black box must be engineered to survive the total destruction of the aircraft. Well, thank you for joining us on this deep dive into the trenches of system administration. Keep your environments patched, rigorously monitor your instrument dials, and never, ever trust a backup that you haven't fully restored. We'll catch you next time on the deep dive.